Welcome to the NPTEL online certification course. The title of this course is Control and Tuning Methods in Switch Mode Power Converter. I am Dr. Shantanu Kapat, an associate professor in the Department of Electrical Engineering, IIT Kharagpur. So, in this course, we are going to primarily consider the control and tuning method in switch mode power converter. This course is somewhat different from conventional switch mode power converter course, and here we are going to cover a wider range of modulation, control, tuning method and some aspect of modeling technique, and also want to show what are the modern trends in power electronics. So, this is the introductory course and this is a 12-week course. So, primary concept which are covered here in this lecture, I want to show what are the recent trend in power electronics, and then few emerging application and what are their challenges. Then I want to summarize like a DC power conversion system and what are the primary blocks, and then what are the primary objectives of voltage and current regulators. Then I want to introduce the overview of this course and what are the reference resources for this course. So, if you look at transportation and electrification, information and communication technology, then consumer electronics, healthcare, space application, robotics, renewable, everywhere we will find power electronics. This is used for energy efficient power conversion, and this acts as an unified theme across many domains. So, power electronics actually touch upon various domains which include the circuit system, electronics, physics, control system, nonlinear dynamics, then electromagnetic, signal processing and so on. So, that is why the interdisciplinary research and development activity. The power electronics is going through a transformational chain where we are going to witness the increasing use of wide bandgap devices, and primary objectives are to operate power electronics converter at higher switching frequency, so that the size of the converter can be reduced. The another objective, of course, this was always there, is to achieve high efficiency, so that the thermal overhead can be reduced. So, in a way we are trying to operate at a higher frequency to reduce size, at the same time to reduce thermal overhead. So, the overall power electronic system and the subsystem in a particular application can be reduced. It is also important that power electronics at present and also in future to meet various stringent performance requirements. So, we need to achieve high performance. Since we are trying to operate at a higher switching frequency, so we have limited time and also limited resources. So, we have a constraint on the resource as well as time. So, we need to use smaller resource yet to achieve high performance. So, we need to achieve high throughput. Switch mode power converters are also they are the source of electromagnetic interference. So, we need to meet certain EMI compliance and harmonic EMI compliance for various applications. For example, in automotive application, space application, where we need to meet stringent EMI compliance, and also we need to reduce the harmonic content. So, as I said, the power electronics we are going to witness increasing use of wide bandgap devices. So, two major wide bandgap devices which are actually slowly becoming more and more predominant in power electronics is the gallium nitride device, which operate which actually the application include the lower power level, but they can be operated at a much higher switching frequency. The power converter using GaN devices can be operated much higher switching frequency in terms of few hundreds of kilohertz to few megahertz or even few tens of megahertz. In other application domain like a high power application, where we are going to witness more use of silicon carbide devices, and these two devices are wide bandgap devices. That means they can withstand higher that voltage breakdown voltage, and also their junction temperature is very high, so that they can operate at a higher ambient temperature, and also they offer lower RDS the on time resistance of the switch. So, the conduction loss can be reduced. And another important factor is that lower gate charge requirement. If we look at the silicon devices, like there is we know about the figure of merit, which is generally considered to be the product of RDS(on) and the QG. So, if you want to reduce RDS(on), then QG goes up. If you want to reduce QG, then RDS(on) goes up. But in wide bandgap devices, it offers unique opportunity to reduce both RDS(on) and QG. So, we can operate at a higher switching frequency at the same time. For a smaller, because of smaller RDS(on), we can also reduce the conduction losses. So, we can reduce both conduction and switching losses. And it also offers negligible reverse recovery problem, which is another major drawback in silicon devices, where we know there are body diodes, and and if we use a synchronous converter, where you use only switching like a MOSFET active devices, the control devices, in which actually we need to provide some dead time, but if the dead time is large, it actually the diode becomes operational, and use of diode as well as the body diode in MOSFET, power MOSFET, they also actually leads to lot of reverse recovery problem. So, these devices, wide bandgap devices, can offer reduced reverse recovery problem. And if you say application domain, like for low power level, particularly for data center application, for class D audio amplifier application, then charger application, robotics application, the wireless power transfer, these are the application where the GaN devices are now becoming like a it's like a attractive solution. Similarly, if you go for high power application, for example, the charging infrastructure, railway application, then like a distribution power electronics, or even battery charger, we can see lot of silicon carbide devices are now becoming more and more like in the commercial product. So, if we take particularly the GaN devices, so now GaN power gallium nitride device, actually they are now entering into a new era. And if we look at the kind of application, like starting here, the projection is taken from Wale development, and it shows that the wide bandgap device like a GaN devices, their market value, like they are going to see a, because of increasing use of wide bandgap devices, the business can reach up to $1 billion or more. So, there are many applications like a data center, as I said, then power supply for low power application. And if we look at silicon carbide device, their application, as I said, their applications are more like a little bit higher power than gallium nitride, because we may not be able to operate at a high switching frequency like gallium nitride devices. So, the application includes like a for silicon carbide devices like a solar, renewable, then a hybrid electric vehicle, then charging infrastructure, then also distribution system. Okay. So, now using such devices, since these devices are becoming more and more attractive or their trend is going up, so I want to show one example. This is particularly like a DC distribution power conversion system in a smartphone. As we know, the smartphone is a common for almost many people, like if you go to village area also, the smartphone becomes a common practice, particularly for post COVID scenario. In a smartphone, you have many features, so which include camera, RF module like a for communication, wireless communication, then lot of storage devices nowadays we can see in smartphone, then display device, then GPU for graphical processor unit, power processing unit, then CPU like a central power processing unit. But there is only one battery source, so we need to generate we need to drive so many applications which require power, but the source is only battery. And if we try to think about what are the unit that are inside a smartphone, so there will be one battery in all smartphone, In fact, nowadays the hybrid battery technologies are coming, but there are multiple applications like for transmission part, signal processing part like a processing unit, then display part. All this part has various subsystem, and various subsystem require various voltage and current levels. And since there is only one battery voltage and that require multiple POL. So, where POL stands for here, this POL this stands for point of load application. So, if we take point of load, so this POL stands for, here it is point of load converter, point of load. So, this point of load power supply POL is used for because this POL they directly supply to the load. So, if we try to visualize what is the power supply network in a smartphone, it has definitely a power processing unit, power management unit, and which process power from the input power is the battery, and output there are multiple unit like a display unit, then there are various sensor unit, DSP units, the computational block, signal processing block, then there is also like a motor, so for vibration, then RF transmission. So, there are various unit various voltage and current level that you can see from different voltage levels. So, it require multiple output with multiple voltage and current ratings, or their requirements are different, but there is only one source, that is the lithium ion battery. But in modern smartphone, like maybe in future smartphone, it is not a single lithium ion technology, or it is not a single battery technology. So, there can be a combination of lithium ion or some other technology, because we need both high power density as well as high energy density. That means the battery has to store more charge for longer battery life for the mobile phone. At the same time, it has to meet the stringent requirement of multiple processing unit in order to if you want to see movie, if you want to talk, then if you want to attend video conferencing. So, such application require faster load transient computation. So, that power supply requirement is different, where you may need high power density energy storage. But if in most of the cases, in majority of the time, the smartphone or your mobile phone is in standby mode, or you want to use very nominal application, then you need high energy density, so that the battery life can be sustained over a long time. But all this require multiple DC voltage regulators in order to meet different application requirement. Now, if we look at data center application. So, in data center, now the data center is common, because everything we talk about cloud, even we want to store data in cloud. So, it is a cloud server like the cloud storage. We want to run certain application in cloud where the actual server is sitting somewhere else. We are browsing so many internet, we are accessing so many storage, for example, in Google storage, Microsoft storage. So, most of these storage devices, actual physical storing element, which are sitting in some data center. So, that means such data center require heavy like a computational, it has to meet heavy computational requirement, storing requirement, and very high bandwidth communication requirement. So, all this require power and very stringent power, and all these application, most of the application require very low voltage high current. For example, for processor application like a cloud server, the voltage can be 1 volt, 1.8 volt, close to that, or even less than 1 volt, but the current can be hundreds of ampere. In fact, future cloud server we can see thousands of ampere, it may be more than 1000 ampere. So, such application where we need extremely high load current, the current demand, and of course, low voltage. So, it require, we need to meet stringent, but that current actually varies based on the computational requirement. And if you see the picture of this cloud server, you can see it is like a rack. So, multiple power supply, like this is one, then another power supply. So, all this power supply kind of a rack. So, it is a plug and play, you can take one then put another. So, they are arranged in a kind of a plug and play module. So, these are the module plug and play power supply, and there should be a feature of hot swapping. Hot swapping means when other modules are active, if you want to interchange one module due to failure or something else, or you want to replace, you can simply take it out and plug in another module without disturbing the overall power supply network. So, that is why that is called hot swapping. But all this require ultra fast transient response as well as high efficiency, because as I said, the currents are hundreds of ampere and they changes in step. That means the current can change from 1 ampere to tens of ampere to hundreds of ampere, and such change of current, the slew rate can be few hundreds of ampere per microsecond. So, there are very this kind of application requires stringent performance requirement, and you also need to achieve high efficiency. So, if the present trend of data center, they require 48 volt, because earlier there are different voltage levels, we start from AC distribution network, then convert that AC to DC, then there are multiple stages of DC, and finally when it comes to the processor, in earlier we generally use two stage architecture like an intermediate bus, where first we convert this 48 to 12 volt and then 12 to 1 volt application. But now actually we are trying to reduce the size of the converter, because if there are two stages, the efficiency of the overall converter will be product of these two. So, in order to improve efficiency and reduce size, the present trend, there is a lot of research going on in various academic institute and also various industry, where it is like a high power density power supply for 48 to 1 volt application. So, sometimes this uses transformer based solution, sometimes we use hybrid DC-DC converter. So, in this course, very just brief, I will touch upon a little bit about this hybrid switch cap architecture, and then we will primarily go to traditional switch mode power converter. So, in such application, the output side, which is 1 volt, it is a low voltage high current, and it has to drive a server or a processor which may require few top tens of ampere, it can be hundreds of ampere. So, generally the output size is multi-phase. So, the current transient step size is pretty large, and we need to meet such stringent performance requirement and also to achieve high efficiency. Now, if we look at power supply network in electric vehicle is another very upcoming area, and in fact, many commercial electric cars are now available, and many manufacturers are actually trying to upgrade the electric vehicle by modernizing their power supply network, and this is particularly using the wide bandgap devices. So, here this electric vehicle have two type of battery, one is a high voltage battery, like you can see this type of high voltage battery, and there can be a lower voltage battery, like in a traditional car we use a 12 volt battery. So, high voltage battery is used to supply the power train, like the drive train, like a motor for propulsion like application, like for vehicle movement, right. So, you need this high voltage as well as low voltage battery, and there are many architecture like a power converter, like a DC to DC converters, here high voltage to low voltage. So, multiple DC-DC converters are required, and this 12 volt, actually this 12 volt battery supply majority of the electronic load in a car, which is common irrespective of whether it is hybrid, plug-in hybrid, fully electric or even conventional car. We have lot of infotainment system, dashboard, lot of electronic gadget which are driven by this 12 volt battery. So, that means we need multiple DC-DC converter, and many objectives are common in terms of performance, efficiency as well as power density size. So, Another application is the fast battery charging. That is also very upcoming, and all people are talking about fast charger, fast battery charger. But this fast battery charger also we need to consider various aspects. First of all, in order to charge fast, any battery, if you take a battery, whether it is a fast or slow charger, whenever the battery is fully discharged, if you see the green line here, this shows the capacity of the battery. If the capacity is very low, that means starting from almost 0, like battery is almost fully discharged, and you can see some terminal voltage when the battery is almost discharged, and every manufacturer, battery manufacturer, they provide in their data sheet what is the voltage level corresponds to almost discharge of the battery, the capacity almost close to 0. So once the terminal voltage reaches to that level, we should not discharge further, because there are certain constant, the battery life will be totally get degraded. So once we come to the limit, then we need to charge the battery, because we cannot use it. So when you start charging the battery up to certain level of voltage, and in majority of the lithium ion voltage, they talk about 4.2 volt. So when you start charging the battery, you see the voltage is actually increasing, this voltage curve is increasing, but initially we generally use a constant current charging up to that until the voltage reaches 4.2 volt. And this constant current charging, what is the amount of current that should be used to charge the battery, that also depends. For example, in our mobile phone, now most of the mobile phone, the charger, one of the terminal is USB terminal. So that USB, either we put it into our plug adapter, or we can actually, we can use that USB and you can connect to our computer also. So in both cases, mobile will be charged either through adapter or through our laptop. But you will find that the total charging duration differ. In adapter, it takes lower, like a smaller duration, and in our laptop it takes longer duration. So this is because of how much current you are using to charge. If you use a lower current, battery will take longer duration to charge, and higher current battery will take, battery will charge faster, but charging faster also you have to pay penalty, because the battery may get heated up, and in fact we need to check whether battery technology will support such fast current charging or not. So there are a lot of optimization, thermal, other aspect, so constant. But when battery reaches 4.2 volt, we need to go for constant voltage charging. That means we need a, the seamless transition between constant current and constant voltage, and this power converter has to meet certain constant current and constant voltage charging configuration. If we go to automotive LED, most of the car or like a lighting system is now going to be like almost going like using LED. So LED, if you take headlight, if you take fog light, if you take tail light, everywhere you will find now slowly increasing use of LED. And this LED are semiconductor device, and they directly operate through DC voltage. But we cannot connect such LED directly to the battery, because LED requires certain current regulation. LED, you need to ensure the current through the LED is going through a controlled manner. So you need a power management circuit, a DC-DC converter based on the voltage and current, and we need to drive such LED here. So if you go for DC, like a power, like a brightness control in the LED, we need to control the current going through this LED, and that we call LED current. So this current, LED has some IV characteristic. So one way to control the brightness of the LED by controlling the current in a continuous fashion. So that means if we reduce the current, the brightness will get reduced. If you increase the current, so this is a constant current control with depending upon what current command you are sending. This is analog dimming, where we are strictly maintaining the constant current. The another dimming technique is called PWM dimming, where the LED current, that means this LED current, I am talking about this ILED current, these currents are operated either at their nominal value or 0. That means unlike in previous cases where the current can be adjusted in between its nominal value to 0 value. In this case, the current is used either 0 or full value, a nominal value. Then if we use, let us say, 1 second fully on LED and 1 second fully off. So, over 2 second duration we will get 1 second on, 1 second off. Now, if we this ratio, if we keep 50% like 1 second on, 1 second off. Now, if we make it 1 millisecond on, 1 millisecond off, the ratio remains same, but the time duration is reduced. So, if we use such a faster change in current, then our eye cannot see the transient moment of the current. That means, I will see like a low pass filter. So, it will see the average value of the current. That means, it will see like a 50% brightness of the LED, and LED are the semiconductor devices. So, we can turn on and turn off very fast, but for our human eye perception point of view, the LED can be turned on and off at a faster rate, and if we adjust the duty ratio of the on and off time, then we can adjust the brightness. So, this is another application where we are using constant current with a step command. Now, LED driving, either we can control this LED current using, we can connect this LED string. So, this is my LED string, we can connect this LED string to a power supply, and we can connect a series resistance to adjust the resistance value, so that the current through the LED is maintained. But this way is not an unique way. So, that this is not a good way, because this change in resistance actually is used to reduce the drop, voltage drop, in order to maintain the voltage across LED as well as the current through the LED. So, this way actually most of the losses, majority of the losses happen through this variable resistance, and it is lossy, efficiency is poor, and we need a bulky heat sink. The alternative approach, we can use a voltage regulator in which this output voltage can be adjusted. Now, the series resistance is constant, unlike in the previous case, but the voltage is adjusted. That means, now we are adjusting like a virtually you are trying to control this voltage by using a voltage regulator. This approach is better than previous, but we still need the efficiency, depends on the efficiency of this voltage regulator, and also, but the loss in the RS is still there. The third approach, we can use directly as a current regulator. That means, the power converter, this is a SMPC, switch mode power converter, which can be used as a current regulator, and where the output of this converter is a control current. So, we do not need to use any resistance here, because we do not need to create any drop. So, you can control current. This way you can achieve higher efficiency, but this, if you want to take care of this combination of voltage and current regulation configuration, then because purely current regulated driving might be a problem when you turn on and off LED between multiple string or multiple time, because of voltage mismatch there can be that can lead to sometime like a flickering current. So, if you take care, combine these two techniques, because the practical current regulator cannot have a pure current, constant current during transient also. So, if you use these two combination, probably we can reduce various drawback of either configuration, and we can take the best combination in this approach. So, the DC power conversion objective, either we need voltage regulator where we need to regulate the output voltage, or we need a current regulator where you need to regulate the load current or the output current. So, that means we need either voltage or current regulator. The voltage regulator output voltage need not to be always constant, it needs to track also in some case of power amplifier application. So, that means the voltage regulator can be, that means power converter can be used for tracking application as well. If we see the transient scenario, I talked about low voltage high current application, where the load step, this load step can be some hundreds of ampere, tens of ampere, and if such load step up, the load suddenly changes from, let us say, from 10 ampere to, let us say, 50 ampere. So, then the converter can actually undergo a large undershoot, and when it step down, large overshoot. So, the typical load profile, the load changes very fast and the slew rate can be few hundreds of ampere per microsecond. This transient can appear frequently because if you use a computational load, the computation depending upon the the instant of computation, the load current can drastically change. So, the transient can happen frequently and we need to reduce this overshoot and undershoot because there is a stringent requirement in terms of noise margin of the voltage, because this power supply is used as a VDD of this digital processor. And you also want to reduce the transient time, that means you need to speed up this transient. So, the primary objective of a DC-DC this course we are trying to particularly focus on DC power conversion system, where we have a DC source and we have a DC load. The load can be either single load, it can be multiple load, but here we are talking about single source. Even in some cases there can be multiple source like for energy harvesting, but primarily we are talking about single source and single load in this course. Then the source can be battery, grid, ultra cap, solar. The load can be if you use in mobile phone, cloud computing, automotive. Either we need to step up from source to load or we need to step down, or it can be close to input output voltage can be close to each other. Either we need to isolate the ground between DC source and DC load, and in some cases we do not require isolation. So, then primary objective, the source voltage can vary, the load current can vary and current can vary in step transient. In some cases the load voltage can also vary in dynamic voltage scaling application. So, our primary objective is to achieve tight voltage regulation in case of voltage regulator, and we also saw some application of current regulator where we need to maintain precise current. For example, in constant current battery charging, LED driving, we need to achieve high efficiency over a wide range of load current and input voltage, and we need to achieve fast transient response, and we need to reduce the size of the converter because everything starting from our mobile phone, the car, everywhere we want to reduce the power processing size and weight. So, we need to achieve high power density and we need to ensure stable periodic behavior in order to predict the ripple parameter. So, summary of the objective for all this discussion what we have considered, we need to identify suitable voltage or current regulator depending upon your application, nature of the application. We need to understand the behavior and we need to estimate the losses, these are also very important. Then our objective is to reduce size for the DC power conversion system, and as I said, that is the growing trend where we want to use more wide bandgap device, and also I will show the control can play a significant role even for reduction in the transient time, transient overshoot undershoot, as well as to improve efficiency and also to reduce the sizes. Control can also play a role. Then we also need to achieve high performance and efficiency, and selection of suitable modulation and control technique is very important, and design and control of voltage and current regulator are critical. So, keeping that in mind, this course is designed for 12 weeks, and this course we are going to touch upon various basic DC-DC power converter architecture, and we will primarily consider non-isolated, but some of this technique can be used for isolated converter also. Then I will also discuss about different fixed frequency and variable frequency modulation technique. I will also discuss various feedback and feed forward control method. I want to give you an overview of modeling and analysis technique. I also want to discuss about small signal modeling, frequency response analysis, then how to design small signal based controller, and also what are the tuning method and their summary. Then I also want to identify what are the limits in order if you want to achieve high bandwidth using small signal based control, and then what is the requirement for going for large signal based control and tuning method, and then we want to show some of the large signal based control and tuning method, and then how to identify critical performance limit. So, for this course the primary references this is a tutorial paper which is an open access journal. This will be a very valuable resource for this course. Then there are very well known books like Ericsson, Maximovic, Professor Ericsson and Maximovic book. That book is also will be needed. You can refer to this book with some of the design and topological aspect. And also Professor Philip Krein, that Elements of Power Electronics book, that can be also very useful for various topics in this course, in particular for the geometric control, the nonlinear control method. And then you can also refer the NPTEL switch mode power converter course, which can be used like a preliminary resources, particularly to understand the topological aspect, the loss aspect, the switching device, magnetic selection, power stage design. In depth you can get the resource. Thank you very much for this lecture.